In computer system, we may have multiple processes running in the system. Sometimes, even single program may need multiple processes to deliver the service. For example, the Google Chrome we just mentioned in the previous slide, for those processes, they may run independently or cooperatively. So in most of the case, processes may run independently, but for some certain situation, the processes may need to collaborate with each other for several reasons. For example, when two processes share the same file, they must have the information sharing. In this situation, they need to cooperate appropriately. Otherwise, they may face the coherency problem. So you may still remember the cache coherence problem, which we mentioned in the previous chapter. Another situation, since we may have multiple cores in a single CPU and multiple CPUs within a computer system, so in order to speed up the computation task, so we may divide the computation task into multiple smaller tasks, and each task is corresponding to a process. So then we can put a different process into different CPUs to speed up the entire computation task. So surely those processes need to cooperate with each other to make sure the correctness, right? Sometimes we may have some very complicated programs. For those kinds of programs, we may want to divide different functionalities of the program into different modules, like what we do for the module architecture of operating system. So for each module corresponds to a process. In order to implement the main goal of a program, each process needs to cooperate with each other. And also sometimes the processes need to collaborate with each other for convenience purpose. For example, the Google Chrome. So you may use one tab to download the content from the web server and use another tab to watch the content of the same website for saving the time, which is quite convenient for the users. So since the processes, they need to collaborate with each other, processes need to exchange the information with each other. So they can use the interprocess communication, which is shortened as IPC, to achieve this goal. There are two generic ways to do that, which are shared memory and message passing, that we have discussed in the previous chapter. So you may still remember that the pros and cons for each way, and for each way in what kind of a situation will be used. For most of the case, message passing is much convenient to use. So that is why shared memory is less common in nowadays operating systems. But within the same computer and under certain situation, for example, the efficiency or the accessing speed to a file is a first priority of a computer system. So shared memory will be used to achieve that goal. Next, let's look at a classical problem called producer-consumer problem, which is widely used to investigate different mechanisms for cooperating processes. The producer process will produce information which is consumed by the consumer process. So normally, this problem will be discussed in two situations. One is an unbounded buffer, which means the buffer used to temporarily hold the information is unlimited without boundary. On the other hand, actually in real world, the buffer is limited and with a fixed buffer size. So for this situation, we call it bounded buffer. In this slide, we are going to talk about the bounded buffer, which uses shared memory to solve this producer and consumer problem. Basically, we can define a memory region that can be shared by producer and consumer processes. So down below showing you the pseudocode. So firstly, we define the buffer size as 10. Then we define an atom type structure. So within the atom structure, we define numbers of information which can be used by producer and consumer. But here, we just abstracted them as a single atom. Then we define an atom array with a predefined buffer size to hold the atoms produced by producer and consumed by consumer. So each element is an atom. And then we define two variables. One is called in, to point to the next available buffer slot, which can be used to hold the newly come atom. Another is called out, to point to the next atom which can be consumed by the consumer. Then let's see the producer program. So within the producer program, we have defined an atom variable to hold the newly generated atom called next produced. And then we have an infinite while loop. Within the infinite while loop, we have another while loop to check whether the atom array has an available slot to hold the new atom. If no, the program will be stuck at this while loop until the new atom slot is available. But if yes, the new atom will be placed on the atom buffer, which pointed by in variable. Then increase the in by 1 to point to the next available atom slot. Then let's look at an example to see how it works. So suppose we have an atom buffer with a size 4. At the very beginning, both in and out variables, they will point to 0. So firstly, we check if the atom slot is available. And then based on this condition, we know that since in is 0, 0 plus 1, mode buffer size is 4, so we will get 1. 1 is not equal to out, because currently out is equal to 0. So this condition is not satisfied. And then, so which means we can place the atom on the buffer and increase the in variable by 1. Then continually put new atoms on the buffer until we put 3 atoms on the buffer. Then in variable will be equals to 3, out variable will be equals to 0. At this moment, we cannot put another atom on the buffer anymore. Some students may ask, so we still have one more slot available, why we cannot put more atoms on the buffer? So you can imagine, if we put one more atom on the buffer, it will fill up the buffer, right? Then in variable has no place to point to, because in has to point to an empty slot. And also, so why we use the mode buffer? This stuff, because we want to maintain a circular array here. When consumer consumes an atom from the buffer, then all out variable will be equals to 1, right? Then this condition, because currently in equals to 3, 3 plus 1 equals to 4, and then 4 mode buffer size means 4 mode 4 equals to 0, which is not equals to out, because currently out is equal to 1. Then the producer can put a new atom on the buffer again. So later we will talk about a new solution which can use all the buffer size. Then let's see the consumer program. In this consumer program, we define an atom variable to hold the new atom moved from the buffer, which is called next consumed. Within the infinite loop, we have another while loop to check whether the buffer is empty or not. If yes, the consumer program will be stuck at this while loop. Otherwise, the new atom will be stored in the next consumed variable. Then increase the out by 1 to point to the next new atom on the buffer. Here actually we use the same trick as a producer to maintain a circular array through the percent buffer size.